All right, so we will we'll close with APIs. And I'll get out of the way. Rob, it's all yours.
All right, thank you. The last keynote. I told everybody when I was doing the last keynote, I said that this audience is going to be nothing but the hardcore leftover nerds who are all going to tell me why I'm wrong. So I look forward to the treat rage. My name is Rob Zazueta. I work with a company called TIBCO. I joined TIBCO when they acquired Mashery, probably one you're a little bit more familiar with, API management tool. Mashery's been around since 2006. We've been to GlueCon before many times. Been a couple years since I've been here. Honestly, I'm really, really tired about talking about computer technology. We've been doing it for the last few days. I'm exhausted. How about you? Let's talk about something different. Let's talk about biology. There we go. Wait, come on. There we go. CRISPR. How many of you have not heard of CRISPR? Okay, good. That's interesting. Okay. So if you've heard of gene editing, that's sort of the simpler way of talking about CRISPR. CRISPR is an acronym. You thought we had a bad in our industry. Clustered, regularly interspaced, short palindromic repeats. Jesus. What does that mean? CRISPR is fascinating. What it's allowing biologists to do is actually change our DNA, strand by strand, individual gene by individual gene. This is not something that technology created. This is something that nature has been doing for millennia. How it works is RNA, which helps to build DNA, helps to build cells, that kind of stuff. Certain types of RNA have these bookended palindromic sequences. So if we're talking about DNA, by the way, this is the high-level layperson's view of this. So if you know more about this, you catch me on wrong. Twitter, Zazueta. But basically what they've discovered is these little bookended sequences that are palindromes. So if DNA is created using, let's say ATGC, I believe are the 4, then if I see ATGC, I would have also seen ATGC, CGTA. I would have seen the exact same sequence backwards. In some cases, they're right next to each other. In other cases, there's a strand of DNA inside of them. But they found this in bacterial cells all over the place. And they think that the reason that this exists is because what these RNA sequences that have that bookended can do is they can do a search and destroy mission for whatever they found in between that bookended sequence. So basically I'm saying, here's a strand of DNA, go out and find it in all the larger strands, and then eliminate it. And the reason they think this is a defense mechanism for bacterial cells is because that's how viruses reproduce. When viruses get into your cell, they start spreading their own RNA and their own DNA. They try to insert that in the DNA of the organism they've infected in order to hijack its mechanism for recreating new cells, so that instead of creating new cells, it creates new viruses until it explodes and dies. So what this does is it goes in and says, we've identified this as a virus. Let's kill this. Now, the biologists have also discovered ways to not only eliminate, but to replace. Now, this allows for really interesting things. Not only can I identify, for example, strands of DNA that might be linked to a specific disease and remove that, I might be able to replace it with something that makes the organism stronger. And this is opening all kinds of new and interesting avenues for medical research that's DNA-based. But there's also relevancy to us. Because if I can store anything within this, why couldn't I store code? And so that's what they've done. This, of course, is the famous sequence of images taken by Edward Maybridge back in the 19th century. Interesting, the reason this exists is because Leland Stanford, had a bet with one of his rich buddies that during a horse's gallop, at one point in time, the feet actually leave the ground. And so he worked with Edward Maybridge. This is before film, before cinema. He worked with Edward Maybridge to develop a method by which they could actually record this and test this. So it's really fitting that they took this image, converted it into a GIF, converted it from a binary GIF into an encoded format using DNA, and then stored that in a cell. And then turned around and retrieved that and recreated it perfectly. That is really cool. That means I can start taking the data that we have and I can start storing it within DNA. And this is really cool because DNA is everywhere. It's in every living thing. It has a huge amount of data density. And so I can actually start storing terabytes, petabytes more into much more constrained, smaller spaces. This sounds some far-fetched kind of future stuff, right? But there's already companies working on this. In fact, in the time that I was putting this together, all of a sudden I just kept coming across all these articles that were talking about companies that were starting to adopt this. This idea that I can use CRISPR not only for medical research and all that, but for computer work too, to store data. At this point, it's primarily about storing, but it doesn't really boggle the mind too far to consider that you might go beyond storing and actually be able to retrieve that and run that code at some point. So in the future, it's entirely possible that some of the code that we write today is going to live in, don't think about your arm or that kind of thing, and that's what a lot of people go to immediately. What they're talking about is tissue cultures and petri dishes in a lab. So it's basically living DNA. That's a living data storage unit for you. Now, I'm not going to help you with the excuse of what you're going to tell the boss when you lost the user database because you forgot to feed the hard drive, but this is our future. And how are we going to access this data? APIs. You were all wondering how I was going to get back to this, weren't you? Of course we're going to use APIs. They're not going to go anywhere. They've been around forever because they are the means by which we communicate with other technologies, particularly digital technologies. But the point here is not just talking about, hey, let's create APIs for DNA. The real point is you don't know where your code is going to live. We've been talking now for, oh God, the better part of 5 years about decomposing our monolithic applications. Actually, that's not true. We've been talking about this for a lot longer because we went from monolithic applications to end-tier applications, and now the big thing we've all been talking about the entire time we've been here, microservices, Lambda, AWS type stuff, function as a service, we're decomposing our code more and more to the point where we don't necessarily know where it's going to live. This is the focus. This is what everybody keeps talking about, microservices. But the reality is, for most companies, this is not what their underlying structure looks like. It's a little closer to this. They're going to be working with their third parties, vendors, partners, third-party data applications. That's where some of their source data is going to come from. Any new application development is frequently going to be done with microservices. And of course, you still have these huge monolithic pieces of legacy that still exist in the system and that we're not going to get away from. I work for a company that legitimately still supports mainframes, COBOL. We have a lot of customers using this, and it's not going to go away anytime soon. Why? Because it works. But the goal is to make that data accessible and to open it up and to find ways to be able to take advantage of some of the newer methodologies of development and put some kind of a layer on top of that to expose it. And that's really what my company focuses on. Now, having said all of that, the next stage of development is function as a service. And I think one of the more interesting places for this is the blockchain. A lot of folks are starting to adopt this. I find Bitcoin boring. I really do. I don't get it. I don't see where the value is. I agree with a lot of the folks out there saying that it's probably basically a giant pump and dump scheme. Ethereum, on the other hand, is fascinating because of the smart contract capability. I can actually write functions and code that live on the blockchain and run on other people's computers. And I am paying for that compute time and just that compute time using the Ethereum currency. That is really, really cool. And while Ethereum may not itself be the future, I think it's at least the basis for what the future is going to look like for shared, massively distributed compute. And we've seen this in action. Right now, it's kind of a toy. By the way, these are my CryptoKitties. They're not currently for sale, but if somebody wants to make me a generous offer, I'll take it. It's been kind of used for toys like crypto zombies, CryptoKitties, all that kind of stuff. I see this developing rapidly into more of a function of as a service network, distributed far more widely. Whether it exists on individual phones or whether it's going to be nodes within your laptop or whether it's going to be servers out there in the world, one way or another, this is the means by which we're going to be able to take advantage of all the distributed compute power that we have that we're currently not really leveraging. Not only take advantage of it in its bite-sized pieces, but pay for it. And I think you're going to start seeing this show its way in your data centers as well. And of course, if this CRISPR stuff and this DNA storage becomes somewhere, you're going to see that as well. So that your data diagram, your data center diagram, starts to look a little messy. We're kind of already at this stage. If you've been paying attention to a lot of the tools, demos that the folks here have been showing, especially the monitoring tools, the stuff that's trying to kind of show you what the network looks like, these are not the kinds of diagrams it's generating anymore. They're generating something that looks a little bit more chaotic, a little bit more like this. Call it a service mesh, call it what you want. And the truth of the matter is, you're not going to know where your code lives. And more importantly, I don't think you should care. We should be offloading a lot of this to algorithms, to CI/CD tools, to the kinds of tools that are going to help optimize for performance, to reduce latency and all of that. And that needs to be taken off our backs even more than it already has been. This, to me, starts to look more like a brain mapping or a cellular network. It doesn't look like our traditional architectures. And I think of it as an emergent architecture. Now, emergence, the way that I use it, this is not an official definition. This is kind of my own definition, but it's basically what it means. It's complex behaviors arising from very simple rule sets. And the classic example is Conway's game of life, which itself has been associated with things like cellular automata theory. Basically, Conway's game of life, every single one of those black squares is a unit. It has a series of rules. I believe there's 6 rules that it has to follow based upon what it sees around it. So if it sees one in the northwest corner, then it should disappear. If it sees one in the north right corner, then it should add a block there. It's very, very simple rules that when put together create these weird patterns. So this is, I can't remember the name of this particular structure, but you can see how they're kind of walking back and forth, and the one on the left appears to be firing a shot that's a walker that's going down. None of that was programmed. This is all just based on these 6 simple rules and where these squares show up. When we talk about emergence, we see this happening in cells, in life, in any kind of weird, complex area. Once we start breaking it down, we can see that actually they start following fairly simple rules. And this should sound familiar to you if you're doing microservices and especially functions as a service. Because we're talking about individual functions, individual pieces of functionality that do one very simple thing that may need to interact with other pieces, other services that are doing very simple things. On their own, there's not much to them. But when you start putting them together, and some very complex behavior starts to emerge, we're currently creating that. There might be down the line, as machine learning and AI gets better, opportunities to automate some of that. And that's when it gets really interesting. But how do I deal with this? I think that if I'm an IT ops person, and I look at this diagram, and I think about this as what my infrastructure looks like, I break out in a cold sweat. How do I monitor this? How do I manage this? How do I know I'm not going to have a cascading failure when this one dot over here crashes? How do I know that the latency is going to be good from one side, from one node on the extreme side to the other? How do I know I'm going to be able to reduce that? It's kind of a freaky prospect. So there's a lot of emerging challenges that come from these emergent architectures. The first, of course, is discoverability. And by the way, none of this is new, right? This is the same problems we've talked about with service-oriented architecture when microservices came up. It's just going to be far more critical now than it's ever been because of the massive size of that distribution. Discoverability is a key piece. How do I know what services are out there and how do I know how to use them? I'm really excited. If you've been following my tweets on the GlueCon hashtag, I am beside myself excited about the stuff I've been hearing about the OAS recently. It's been a while since I've played with Swagger documents in the Swagger format, and to see how it's now migrated basically from a documentation descriptor format to the lingua franca of how we describe services and share them and configure them. I mean, that's where it's going. I think, to my mind, that is one of the key pieces of success for discoverability. And that means that every individual service needs to own their own description. And they need to share that and register that with somewhere in the middle or some other folks. Make it easy for them to be discovered. Tools like Console also make it easier for you to find out where they are, what kind of services are available, and you can share that information as well. Security. How do I know that each service is going to be protected as much as the entire system? Well, massively distributed authentication, where every single service is responsible for their own authentication, that's a headache. That's going to be very difficult to manage. So you still need to keep that centralized. But you can take the authorization piece and make that localized. I think that's probably the right approach. And you treat that authentication as a service using the same APIs to access that information about who's logging in. The JOT tokens are a really good way of exchanging that data. I know there's a lot of complaints about that, but I think that's the right path to go down. And then when we talk about latency, how do I make sure this stuff is going to work properly? I'm going to get the kind of responsiveness. Streaming protocols already exist, WebSockets, that kind of thing. I know you can do gRPC calls over common live-long sockets. What do you call those? Persistent sockets. Over persistent sockets. So that's one way of doing it. Asynchronous processing is the better way probably for a majority of services, especially as you're starting to work them down. But there's a lot of ways to handle this. So again, if you spent the last few days talking to the vendors, going to the sessions, a lot of people are presenting solutions. There's a lot of ideas out there to help fix this. The one that I like the most, though, is the concept of the micro gateway. The micro gateway is a small piece of code that actually lives within your package service. So it would more than likely live within your container. Your code interfaces with the micro gateway not through some kind of agent SDK or anything like that, but through native REST or a native protocol language that's just shared within that container. And then the gateway is the exposing piece to everything outside of that container. This means that I can put a lot of that administrivia on the gateway's back. Authorization, how do I call for authentication? How do I handle logging? How do I handle firing off other services into more of an event-driven architecture? Because that's another way to make things go faster. You know, I make one call, it's going to make a cascade of calls throughout that entire network in order to get the data it needs into updates internal systems, right? So being able to have that handled in a single location and allowing your code to just do what the code does, that to me is the best form of isolation. And of course, it doesn't hurt that, again, the company I work for, TIBCO Mastery, agrees with me on this. So we've come out with our own solution for this. It's called Project Mashling. It is open source. It is built in Go. It is built on top of another open source product that we've developed called Flogo. It does have an ultra-light and embeddable binary that it creates. So compiles that go down to a very, very small binary that can live within your service. It can actually live within Amazon Lambda. So if you want to use our tools to create a recipe and generate that and throw that up in Amazon Lambda or any other function as a service, it can run that as well. It is event-driven by design, so it knows how to cascade that information, how to handle queues, all of that. That's part built into the gateway with the recipes there. Complements a service mesh. You don't have to, it's not tied to any specific vendor. Even though it is created by TIBCO, it's part of the TIBCO Mastery family. It's open source and vendor agnostic. So it doesn't really matter whether you're using a Kubernetes cluster or Docker or what have you. This will work just fine with that. And then, of course, if you are using Mastery, you can very easily publish those APIs to it and eventually start using Mastery as more of a command and control for your distributed services. It works in a bunch of different ways. As I said, the way that I prefer is to actually bundle it with the service itself. That, to me, adheres more closely to the idea of isolating your services, keeping them decoupled, and keeping them independent. They can maintain those recipes locally. You can have a decentralized, or I'm sorry, you can have a centralized configuration and have that then sent out to your individual services. That way you can monitor it in one place. But of course, the gateway will then go ahead, the micro gateway will go ahead and fetch that and hold on to that. But you can also do it as a sidecar pattern as well. There's a lot of different ways to do it. It's not prescriptive in how you use it. And as I said, it is open source, and it's currently being worked on by TIBCO. It is sponsored very heavily by us. But we are inviting other folks to come in and check it out and to add to it and really fit it to your use case. Because as these services do grow, and as you go out there and you have to start concerning yourself with discoverability and security and latency and event-driven models and all this, you're going to need the tools to help you. And this is one of the first tools to come out that can really do that. So I encourage you, visit mashing.io. I'll be around for a while if you have any questions. And Eric, you out there? Because they just brought us back on time. Right on. Thank you very much. Appreciate you guys hanging out.
Thank you, Rob. I love it when a plan comes together.
I love it. Thank you.